Hi, Nate Holmes here. I'm going to take you through an overview of the National Instruments Machine Design Demobox. You can see I have my project open and I'm connected to my CompactRIO. And I have three main VIs in this project. I have my API example, which is the high-level application code. I have my Axis interface, and I have my FPGA VIs. My Axis interface really acts as an intermediary or a transfer mechanism to get data back and forth between the FPGA and the API example through these two Axis objects. I have my AKD, which is a brushless servo drive, connected to a 9516 drive interface module in the CompactRIO, and I have my 9501, which is a C-series stepper drive connected directly out to a stepper motor. Let's go ahead and take a look at the FPGA and what's running there. So this is my FPGA front panel, which is really just a massive controls and indicators, because I'm using this to communicate back and forth to my other objects. And in the block diagram, I really have two sets of code. I have one set for the stepper axis and one set for the servo axis. So let's start with the stepper axis. I'm synchronizing to the RIO scan, which is the mechanism that we use to transfer data at this rate between the FPGA and RT. So I have my synchronization loop here. I have my position loop where I get my spline data and my profile mode, and then go ahead and use the spline engine to output step data. Okay, that step data is then used in the stepper loop to output step and direction signals using the stepper generator IP. I've got a drive status loop to look at enable faults and configuration, as well as some optional loops here. So I have an encoder loop because I have an encoder on this stepper. It's not strictly necessary. I can run my stepper in open loop mode, but I have it here in case I do want to use this encoder in my application code. And finally, I have the motion I/O loop, which looks at all the limits in my system. So on the stage, for the stepper as well as the servo, I have both a forward limit, a reverse limit, and also a home limit. And this is the code to detect changes on those limits, and then pass the data up to the Axis through the Axis interface appropriately. So that's all my stepper code in the FPGA. I've also got code for the 9516 drive interface module. Normally you could run this module without writing any FPGA code through just normal scan mode, or you can run it in FPGA mode and actually close your loops on the FPGA target. If you run it through scan engine without writing FPGA code, you'll close your position, velocity, and torque loops on the external drive, in this case the AKD. If you run in FPGA mode, what you'll do, or on-bound axis mode, is you'll actually move the position and velocity loops up onto the FPGA, or those high-level control loops, and actually just run the AKD in torque mode and send torque commands down to it. And that's what I'm doing here with this example. I've also got some code here for force feedback, so I'm reading from a 9237, the two load cells, which are behind the springs on the actual setup, and I'm reading those two channels and then doing some scaling to output my force applied to those load cells through the spring. I've also got some timer configuration and sync configuration, and then some code to switch between position feedback and force feedback. At this point, we only have position feedback working. I'm working on getting force working. Most of the building blocks are here, as you can see in the code, but we're still working out some kinks in how to write that into the application. So you can see that I do some spline interpolation, and then I decide whether to use either position feedback and position gains, or my force feedback and my force gains, and then those are fed into a PID motor control VI, and then I output a current set point. Do some scaling, and then there's my drive command. Okay, and then this bottom loop, the module interface loop, is just used to transfer all the settings and data back and forth between the module and scan from the FPGA up through your axis to your application code and back down again. So you can see I have my configuration where I have all the parameters. I've got initialization, which doesn't do anything in this case. And I've got my fault safe op and active op. So this is just the module states. And then in this case, I'm reading and writing. I'm writing down all the these variables, scanning, and then reading everything back afterwards, and then I'll repeat this over and over. And then finally I have just a state change VI down here, and that's the FPGA code. So again, a couple loops for the stepper axis, a couple loops for the servo axis, and we're done. And so moving up to the axis interface, this is where all those controls and indicators are read and written to, and then interface to your actual axis object in the project, so either the AKD or the 9501 axis. So let's take a look at this VI. This VI calls the FPGA VI that I just showed you and gets it running. And then we transition into the state machine, which looks at the scan engine state, whether I'm in active or whether I'm in configuration mode, and manages the transitions. I have a watchdog timer here, as well as some globals and some logic to stop the loop if I need to. And then a couple different module states to go through and make sure everything's synchronized. The important state here really is the active state. This is where the bulk of the code happens, and this is where I read data back from that FPGA, update my axis object. So I have my axis coming in here with my configuration for 9501 on top, and an AKD on the bottom. And so I read data, update my spline, update feedback, my limits and homes, and then write data back out to the FPGA. And this happens synchronized to the scan engine. You can see I'm doing that for both axes. And while this VI is running in the background, and as long as I've transitioned appropriately to the right state, I can then run, it's running my FPGA VI, this VI is running in the background, and I can run my high-level application code and program a very complex and customized motion system at a very high level still, and be able to dig down and customize as needed. So let's go ahead and run this VI. You can run this as a standalone VI, and then run separate examples that use axis objects as references, and it will work as long as this has got the FPGA running and transition to active mode. Or you can use this VI in the background and use the interactive test panels with the axes. So you can see that I've transitioned to active mode, and I have my my loop iterating. I've also have indicators here that read values back from my load cells. So as I press on a spring, you can see my 4 servo axis is increasing. I'm not really putting 200 pounds on. I need to change some scaling there. But all the building blocks are in place to do force feedback if I need to. I can also set my microstepping rate and my current reduction, etc. settings for my 9501 here. So now that this is running, I can go up to my 9501, go to my interactive test panel, and enable a drive and command moves, and you can see that I will actually get my moves out. I can even monitor home and limit switches here. So if I do a move that's well outside the bounds that I know I'm supposed to be running in, I can then monitor my my limit switch here. And so I'll go until I hit my forward limit and stop. And so I know that this axis is working correctly. I'm going to go ahead and back off that limit switch. And that's my profile. Let's go ahead and use the AKD as well. So I've moved my AKD. I've actually hit my reverse limit on that move. So I'm going to go ahead and move off that limit. And there's my move profile. So my AKD is working as well. I'm going to go ahead and disable that drive. And so you can see that once this is running in the background, I can use that high-level interactive test panel with both my axes. I've verified that both of them are working. And now I'm ready to go ahead and run some axis interface. I'm ready to run some API, high-level API code on top of all this this infrastructure code. I could go ahead and just drop down an example VI, like a multi-axis coordinated move, change my references for the axes to these two and my parameters for my move profile, and it would work at a very high level on top of this if I wanted to. What I'm going to do is actually show you how to integrate the axis interface VI into a high-level VI. So all you have to do is go ahead and call your API example and not run this in the background every time. So go ahead and stop that. I'll go to configuration pre-op. And then I should be all set and stopped. So let's go ahead and run the API example VI. Now that we've explored the infrastructure behind the axis at the lowest level, this is where you work kind of at the application programming level. You can see I have a pretty front panel here, and I have my actual application code. And this is split up into 4 loops. Before we go to do that, you can see that I'm calling my axis interface VI and just letting it run in the background, and that in turn is calling my FPGA. So I let that get started first. I go through an init state. That init state will just wait until my axis interface code is up and running, and then will return me to an idle state, which basically waits for a command from the front panel before doing anything else. And this is how I go through and do all the different things I want to do with this application example. So I look for a button press on the front panel. So for instance, if I press one of my buttons here to jog backwards or jog forwards or do a home move, it'll recognize the right one and move me to the right case here. So if I want to do a find reference move, I'll go here. If I want to do a coordinate move, I'll do a coordinate move, etc., etc. So that's my main state machine, is this middle loop here. The top loop is my implementation of vision guided motion. So I have a separate loop running to continuously take images and process those images. And then if I have vision guided motion enabled, I actually go ahead and run a straight line move continuously every loop iteration. I update a new position based on this PID loop. And this PID loop is based on acquisition from the camera and some image processing happening here. So that's my vision guided motion loop. I have my main application loop to do coordinated motion, jogging, find reference. And then finally I have my just monitor and graph position, velocity, and some of the indicators in a separate loop that's running at a much slower rate. And finally I can preempt a move and stop the axes here. And this is also running in separate loops, so I don't have to wait on a move to finish before I can go ahead and stop whatever's happening. So that's my high-level API example. Let's go ahead and run this. So when I run this example, we'll get into actually a demo script here. So I run this example, and it'll go ahead and initialize everything. It has to get the FPGA running. It has to go through all that axis interface code. So when I first run it, I'll be in this init state for a little while, and you can see that things are starting to get initialized. And I'm waiting for my scan engine state to switch to active. When I switch to active, you can see I go into the idle state and I run my axis interface code here. So everything's up and running. I can enable my axes, and then to make sure that those are working correctly, I can do a jog backwards and forwards. You can see the front panel updating. This is a live image of the stages. as well as a graph showing position and what would be a 2-axis and X and Y stage. If these were coupled as an X and Y stage, this is what it would look like, and you see the graphs of the position and velocity up above. Go ahead and home my axes. I'm going to go ahead and clear the graph. Oh, I'm sorry, I'm going to reset my position, clear the graph, and now I'm kind of zeroed out and initialized and ready to start the rest of my code. So again, first you go to status, get yourself into active mode, and then go and reinitialize position if you need to, and then clear graphs, and I'm ready to start a move. So I'll go ahead and do some coordinated motion first. I've got both axes enabled. I can go ahead and do an arc move. This is I'm set to pattern right now, which will just do a series of arcs with both these axes in a coordinate space. And I'll go through some pretty code here, and you can see the position and velocity update as I go through this series of moves. And this is the pattern example. And you can see my vision code is always running in the background, so I'm always computing the distance between these two front edges and these ROIs. I'm actually using that information right now, but I am graphing and plotting it. I'll use this information when I go into my vision guided motion case. So you can see I'm doing consecutively smaller arc moves to do circles. Okay, and my move stopped. I can also do a single axis, or I'm sorry, a single arc move. So if I want to do a very small arc move, just do something like this. And that's my single arc instead of a pattern. I can also go back and home these guys again. Go ahead and clear my graph and do a single axis contour move. So I'm going to do this with the AKD. I'll turn my amplitude down a little bit. And you can see as I start my contour move, I'm actually doing a sine wave for 4 iterations. And it doesn't stop exactly on, because of the way I'm generating points, it doesn't stop exactly on the position it started, but it's pretty close. And I can change my amplitude. And my frequency. And so you can play around with settings here, but you're basically doing generating a set of points for a sine wave and then outputting that to the AKD axis. I can also gear my stepper axis and my servo axis together and do a contour move as well. I'm going to leave that be for now. You can get the picture. Okay, now on to vision guided motion. So before you enable vision guided motion, you need to look at making sure you reinitialize the PID, because that's been running in the background the whole time. You want to make sure you don't build up any gains. Right now we have only proportional gain, so it's not really a big deal. You're not winding up your integral gain in the background, so that should be fine. I've got my velocity and my acceleration set here. These values should be fine to give you a nice sharp move. You can change them if you want to. And then once I enable VGM, I'll actually be doing PID on the difference between these two front edges. So I detect edges in, if you're looking at the screen, from the right to left direction. And so I detect the front edge of both of these and then compute the difference between them. And what my PID loop is doing is trying to drive that difference to 0. So my set point is always 0. And my process variable for the PID is going to be that difference. So the area is bounded in that red box between the stages. So let's go ahead and enable this vision guided motion. You can see that my servo axis jumps to align itself with the position of the stepper axis. If I move my stepper axis by jogging it, you can see that my AKD axis follows that axis according to the control loop. So I'm just going to go ahead and move my stepper axis back out of the way here, give my servo room to run back and forth along the travel, and look at, you can see my PID gain and PID parameters graphed here, and you can also look at frames per second. So I'm acquiring it around 50 and I'm processing it around 23 because of all the extra code that's going on in the background. So if I go ahead and introduce another line, I can actually follow something other than that stage. So I can put my finger into the frame, and I can actually control the position of the stage as I move my finger back and forth. The stage will find it. Bring it up here, press the spring, it's not going to make much of a difference. And you can see that's vision guided motion. I'm finding both edges, computing the difference, and doing it on PID loop. You can see my process parameters there, the PID parameters graph. And if I remove my finger, it goes back to this fine edge over here. I have my PID initialized there. As you can see, I forgot to initialize it, so it was initializing the PID every loop. But since I'm only in proportional right now, it didn't make much of a difference because I'm not winding up my integral gain anyway. I found that proportional only is working just fine for this. I'm going to leave it that way. Feel free to play around with the PID gains as you see fit. So I'm going to disable my vision guided motion and go back, and now you can see I'm still detecting that difference. I'm not actually moving my stage to do anything with it. I can just go ahead and jog and do home routines as normal with vision guided motion turned off. Reset my position, clear my graph, and now I'm back to where I started, ready to do other things with this example. If you get to a point where you throw an error and fault the drive, say by trying to move too fast on, say, a contour move, so I can set my amplitude really high and my frequency really high. You can see I actually faulted my drive out after trying to hit a certain position. Once that happens, I can just disable my axis, enable it again, and look at my status. And if you get into a state where you find that you're faulted, you can disable, enable, and you should be able to get back to a running state. If it's the case that does not work, and there's a actual scan engine fault or something that has happened, you can go to the status tab, reinitialize SoftMotion. It'll actually go ahead and clear out all the parameters that SoftMotion has set, and go back to active, and then you should be ready to go after reinitializing SoftMotion. I have a force feedback tab here. Force feedback is not implemented yet. Through an API example, I hope to do that soon. And that is the machine design demo box, from project configuration to exploring the FPGA VI, the access interface VI, and API example, running through some different types of examples, from coordinated motion to simple find reference and jog moves, straight line moves, to advanced vision guided motion application. And you can use this demo box to demonstrate some very advanced concepts, or you can go ahead and use just the access interface running and open up a very simple example and run that coordinated move as well. It's very flexible, and you can choose to run a demo script based on your audience, the time allotted, and the details you want to get into. So enjoy, and let me know if you have any questions. Thanks.